Your kid asks how Siri knows what they're saying, or how their phone recognizes their face in photos. You give some vague answer about computers being smart, but here's the truth. Those systems aren't following a massive instruction manual. They learned. They got better through practice, mistakes, and adjustments, kind of like your kid learning to ride a bike. That's a neural network at work. My name is Kazuki Tanaka, and I've spent years helping families set up home STEM labs where kids can actually build these systems themselves.
You're listening to the STEM Lab podcast. Quick heads up, everything you're about to hear, the research, the data, the script, that's all human work, verified by real authors. The voice you're hearing, though, that's AI generated. Just want to be upfront about that. If you've been listening for a while, thank you, seriously. It means a lot that you keep coming back. And if this is your first episode, welcome. You're in the right place if you want practical, no-nonsense advice for teaching STEM skills at home. We release new episodes every Monday, Wednesday, and Friday. So here's what we're diving into today. Neural networks for kids. Not some dumbed-down version, the real thing, explained in a way that actually makes sense.
So what actually is a neural network? Here's the straightforward definition. A neural network is a computer system designed to recognize patterns by mimicking how neurons in our brains connect and learn. Instead of following rigid if-then instructions like traditional programs, neural networks adjust their internal connections based on examples. They learn from experience. Think about how you recognize a dog. You don't run through some mental checklist like 4 legs, check, fur, check, tail, check. Your brain instantly fires off dog because millions of neurons activate in patterns that were shaped by every dog you've ever seen. Neural networks work the same way. They process information through layers of connected nodes, which are artificial neurons, and they keep adjusting the strength of those connections until patterns emerge. In practical terms, neural networks are powering voice assistants that understand spoken commands, photo apps that sort pictures by face or object, recommendation engines suggesting videos, and game AI that adapts to how you play. The breakthrough isn't that computers suddenly got smarter, it's that we stopped trying to program every single rule manually and instead built systems that learn rules from data. When this concept clicks for kids, they realize they're not studying some abstract future technology. They're understanding how half the apps on their devices already work. And this matters for your home lab because neural networks represent the bridge between traditional block-based coding and actual AI development. Kids can start experimenting with these concepts using Python, Scratch extensions, or even physical demonstrations before they ever touch deep learning frameworks. Now let's talk about how neural networks actually work. I'm going to walk through this using a concrete example, teaching a neural network to recognize handwritten numbers. I like this example because it's visual, testable, and maps directly to activities you can do at home. The architecture has 3 main parts. There's an input layer, hidden layers, and an output layer. The input layer receives raw data. For handwritten digits, imagine a 28 by 28 pixel grid. That's 784 tiny squares, each with a brightness value from 0, which is white, to 255, which is black. Each pixel becomes one input neuron. The network doesn't see a number the way you do. It sees 784 numbers representing shades of gray. The hidden layers, usually one to several, process these inputs through weighted connections. Here's where the magic happens. Each connection has a weight, which is just a number that might start random. Each neuron in the hidden layer calculates a weighted sum of its inputs, then applies what's called an activation function that decides whether to fire. Think of it like voting. If enough strong signals come in, the neuron activates and passes information forward.
The output layer produces the final answer. For digit recognition, you'd have 10 output neurons, one for each digit 0 through 9. The network's guess is whichever output neuron fires strongest. Training is where learning happens. You show the network thousands of example images with labels.
This is a 7. This is a 3. For each example, the network makes a guess, probably wrong at first. An algorithm measures how wrong the guess was. That's called the loss. The network adjusts weights throughout all layers to reduce that error. Then you repeat for thousands of examples. This adjustment process is called backpropagation. The network literally works backward through layers, nudging weights bit by bit. After seeing thousands of examples, patterns emerge. Sharp vertical lines plus a horizontal top usually means 7. The network never explicitly learns that rule. It emerges from adjusted weights. I've run this exact exercise with middle school students using Python libraries, and the moment they watch accuracy climb from 10%, which is random guessing, to 95% over a few minutes of training is when neural networks become real for them. They see the learning curve on screen. There are a few key technical concepts worth knowing for your lab setup. Epochs means one complete pass through the training dataset. You typically train for multiple epochs. Learning rate is how much to adjust weights each step. Too high and the network overshoots. Too low and learning takes forever. Overfitting is when a network memorizes training examples instead of learning general patterns, like a student who memorizes answers without understanding concepts. For hands-on learning, you don't need GPUs or cloud computing for basic neural networks. A Raspberry Pi 4 running Python with TensorFlow Lite handles digit recognition just fine. Check the link below to see the current price on a Raspberry Pi 4 Model B with 4 GB RAM. That gives you enough horsepower for educational neural network projects without requiring internet connectivity once libraries are installed. The difference between this and traditional programming? With traditional code, you'd write rules. If the top right quadrant is mostly dark and the bottom left is mostly light, guess 7. With neural networks, you provide examples and let the system discover its own rules through weight adjustment. That's the fundamental shift kids need to grasp. Moving on to why neural networks matter for kids. Understanding neural networks isn't about preparing your child for a career in 2040. It's about giving them literacy in technology that already shapes their daily decisions. Every time YouTube recommends a video, every time their phone unlocks with their face, every time a game adapts difficulty to their skill level, neural networks are working behind the scenes. From an educational standpoint, neural networks teach 3 capabilities that transfer across STEM disciplines. First, pattern recognition and data thinking. Kids learn that intelligence, artificial or natural, emerges from processing many examples, not from memorizing rigid rules. This mental model applies to everything from understanding scientific experiments, where more data points equals better conclusions, to debugging code, where you look for patterns in what works and what fails. I've watched this shift happen in my makerspaces. Students who grasp neural network basics approach problem solving differently. They start asking, what patterns am I missing, instead of, what's the one right answer? Second, exposure to industry-standard tools. Unlike many educational toys that teach proprietary languages or closed ecosystems, neural network learning paths use the same tools professionals use. Python with TensorFlow or PyTorch, Jupyter notebooks for experimentation, real data sets from sources like Kaggle or MENST. A 12-year-old following AI project tutorials is literally using the same software stack as a data scientist. There's no kiddie version to unlearn later. Third, understanding AI limitations. Kids who train neural networks quickly discover what AI can't do. They see overfitting happen. They watch models make hilarious mistakes on edge cases. They learn that AI isn't magic, it's math with adjustable weights that only works when you feed it good training data. This demystification is critical for the generation that will decide AI policy, ethics, and applications. The skill-building progression matters. Neural networks explained effectively for kids requires foundational competencies, basic programming logic, comfort with variables and loops, understanding of coordinate systems for image data, and statistical thinking, like accuracy and error rates.
This naturally fits after kids master block-based coding and before they tackle advanced topics like supervised versus unsupervised learning. Practically speaking, entry-level neural network projects become accessible around ages 10 to 12 if the child has prior coding experience, or 13 to 15 for absolute beginners. The key milestone: can they understand that a variable can hold not just one number, but an entire list or grid of numbers? If yes, they're ready for input layers. Now let's look at types and variations of neural networks. Not all neural networks work the same way. Different architectures excel at different tasks. Understanding these variations helps you choose the right learning projects and explains why some problems that seem simple to humans challenge even powerful AI.
Feed-forward neural networks, sometimes just called standard neural networks, are what I described earlier. Information flows one direction from input to output. These work great for structured data where inputs don't have a time or spatial relationship. Use cases include predicting housing prices from square footage and location, classifying iris flowers by petal measurements, or recognizing handwritten digits. For kids, these are the best starting point because the architecture is straightforward. Data goes in one end, answer comes out the other. Convolutional neural networks, or CNNs, add a crucial feature. They look at spatial relationships in images. Instead of treating every pixel as an independent input, CNNs use filters that slide across images detecting local features like edges, corners, and textures. Early layers might detect simple horizontal lines, while deeper layers combine those into complex concepts like eye or wheel. CNNs dominate computer vision tasks: face recognition, medical image analysis, self-driving car perception. Kids notice the difference when they try using a standard network on images and get mediocre results versus a CNN where suddenly it works. Recurrent neural networks, RNNs, have memory. They process sequences by maintaining an internal state. This makes them perfect for time series data, text prediction where each word depends on previous words, speech recognition, or stock price forecasting. The network remembers context. For kids, RNNs unlock fun projects like training a model on their favorite book series and having it generate new, nonsensical but grammatically plausible paragraphs. A variant called LSTM, long short-term memory networks, solve RNN's biggest problem, which is forgetting important information from way back in a sequence. Generative adversarial networks, GANs, pit two networks against each other. A generator creates fake data, say images of faces that don't exist, and a discriminator tries to spot the fakes. They compete until the generator gets so good the discriminator can't tell real from fake. GANs create those "this person does not exist" AI-generated faces and deepfakes. For kids, GANs are conceptually mind-bending but computationally expensive, better as a demonstration than a hands-on project until they're comfortable with standard networks. Here are the practical implications for your home STEM lab. For ages 10 to 14, stick with feed-forward networks and simple CNNs using pre-built libraries. The Teachable Machine project from Google lets kids train image classifiers in a browser without writing code. They see CNN behavior without infrastructure headaches. This prepares them for text-based implementation later. For ages 15 and up, Python with TensorFlow or PyTorch opens up all architecture types. Check the link below to see the current price on a CanaKit Raspberry Pi 4 starter kit. That provides enough computing power for educational projects, though anything involving large image datasets or GANs will eventually benefit from cloud computing credits. Google Colab offers free GPU time for learners. The progression path: start with classification problems using feed-forward networks, move to image recognition with CNNs, then tackle sequence problems with RNNs. Save GANs for kids who've built 5 or more working models and want to explore generative AI. Each architecture teaches a different aspect of how we model intelligence: classification, pattern recognition in space, pattern recognition in time, and creativity through competition. Let's tackle some frequently asked questions. Can my child learn about neural networks without advanced math skills? Yes, kids can understand neural networks at a conceptual level and build working models without calculus or linear algebra. Modern libraries like TensorFlow and PyTorch handle the math automatically. Your child writes high-level instructions like add a layer with 10 neurons or train for 20 epochs, and the library performs backpropagation behind the scenes. They should be comfortable with basic algebra, variables, and simple equations, and understand percentages for accuracy metrics, but they don't need to manually calculate derivatives. I recommend starting with visual tools like Teachable Machine or Scratch ML extensions, where they see cause and effect. Adjust architecture, watch accuracy change. Then transition to Python when they're curious about what's happening under the hood. The deep math becomes relevant if they pursue computer science in college, but it's not a prerequisite for understanding concepts or building projects.
What equipment do we need to start experimenting with neural networks at home? A mid-range computer or Raspberry Pi 4 with 4 GB RAM, a webcam for image classification projects, and free software will get you started. Total investment under $100 if you already own a computer. For software, Python 3.9 or higher with TensorFlow or PyTorch, both free and open source, covers most educational needs. Kids working on image projects benefit from a decent webcam for real-time testing. Check the link below to see the current price on a Logitech C920 HD Pro webcam. That works well for training custom object detectors. Internet connectivity matters during initial setup for downloading libraries and datasets, but many projects run offline once configured. Storage requirements are modest, 5 to 10 gigabytes for Python, libraries, and several practice datasets. Processing power determines training speed, not capability. A budget laptop will train digit recognition in 10 minutes instead of 2 minutes on a gaming PC. Projects scale beautifully. Start with CPU-only training on small datasets, then explore free cloud resources like Google Colab when kids tackle larger problems. No subscriptions required. All the industry-standard tools are open source. How does learning neural networks connect to other STEM skills we're building? Neural networks sit at the intersection of programming, mathematics, and data science. They're a natural next step after kids master Python fundamentals and want to apply coding to real-world problems. The skill progression typically flows block-based logic, text-based programming, data manipulation, machine learning, neural networks. Kids use programming skills to prepare data and build models, apply mathematical thinking to understand accuracy metrics and error analysis, and develop engineering judgment to debug why models fail. Neural network projects reinforce concepts from other domains. Training on sensor data from Arduino robotics projects teaches them how robots could learn from experience instead of following pre-programmed paths. The critical connection is that neural networks transform coding from telling computers exactly what to do to teaching computers to find patterns themselves. This conceptual shift prepares them for advanced work in AI and machine learning across virtually every technical field.
Are there screen-free ways to teach neural network concepts before jumping into coding? Yes, you can demonstrate core neural network principles using physical games and analog activities. I've used these with kids as young as 8 to build intuition before screen time. Try this. Create a human neural network where each child is a neuron. Give them cards with simple rules like, if most of my neighbors say yes, I say yes. Feed data to input children by showing them shapes. Watch information propagate through layers. See what output children decide. Adjust rules, which are weights, when the network guesses wrong, then repeat. Kids physically experience how distributed processing and weight adjustment enable learning. Another approach, use sorting activities with items that have multiple attributes like color, size, shape. Kids build if-then rules to sort them, then discover their rules fail on edge cases. This introduces the concept that learned patterns work better than rigid rules for complex problems. Board games like Mastermind teach pattern recognition through feedback loops. These screen-free activities build the mental models that make neural networks click instantly when you move to actual coding. They're especially valuable for younger siblings who watch older kids program but aren't ready for Python yet. What's the difference between neural networks and machine learning? Are they the same thing? Neural networks are one technique within the broader field of machine learning. Think of machine learning as the toolbox and neural networks as one particularly powerful tool inside it. Machine learning refers to any system that improves performance through experience rather than explicit programming. This includes decision trees, support vector machines, random forests, and many other algorithms. Neural networks are a specific approach inspired by brain structure. The relationship matters for learning progression. Kids should explore simpler machine learning concepts first, teaching a model to classify flowers based on petal measurements using decision trees, for example, before tackling neural networks. Simpler algorithms are easier to visualize. You can draw a decision tree on paper. They train faster and make their logic more transparent. Neural networks become necessary when problems involve high-dimensional data, like images with millions of pixels or audio files, or complex patterns that simpler algorithms can't capture. Our guide to machine learning fundamentals covers this progression in detail. For practical purposes, start with machine learning as the concept, introduce neural networks as a powerful machine learning technique for especially complex problems, then explore supervised versus unsupervised approaches as their understanding deepens.
Let's wrap this up. Building neural network literacy, neural networks explained successfully for kids, means they understand three core ideas. Computers can learn from examples instead of following rigid rules. Learning happens by adjusting connection strengths through repeated exposure to data. And AI isn't magic, it's pattern recognition, with strengths and spectacular failures. The practical learning path starts with conceptual activities around age 8 to 10, moves to visual training tools like Teachable Machine around 10 to 12, then progresses to Python-based model building by 12 to 15, depending on coding experience. This isn't a toy topic. Kids who grasp neural networks are using the same frameworks, the same data sets, and the same debugging approaches as professionals. The ceiling is as high as their curiosity and math skills can take them. I've watched 11-year-olds train image classifiers to sort Lego pieces for robotics projects. 13-year-olds build gesture recognition systems for homemade game controllers. And 15-year-olds tackle real Kaggle datasets for competition submissions. The capability progression is steep once foundational coding skills are in place. Start with one classification project, handwritten digits, rock, paper, scissors from webcam images, or audio command recognition. Let them experience training and testing. That first successful model where they watch accuracy climb and then test it on new data transforms neural networks from abstract concept to tangible tool they can build with and deploy.
That's it for this episode of the STEM Lab podcast. Thanks for sticking with me through all of that. New episodes come out every Monday, Wednesday, and Friday, so you've always got something to look forward to. If you found this helpful, I'd really appreciate it if you could leave a 5-star rating and write a quick review. It's one of those things that actually matters because it helps other parents and educators find the show when they're searching for this kind of content. And if you haven't already, go ahead and subscribe or follow so you get notified the second a new episode drops. Catch you next time.